Alright, welcome back. You know, as I look there at Lambert-Beer's law, I know not everybody's nuts about equations that have an E in them. That's that Euler's E on your calculator. It's like that EXP button. If you're not clear about what to do with E or EXP or whatever, let me know. That's the kind of thing we get sorted out. Okay, I'm okay explaining that to you. I just don't want to do that right this second on YouTube. So in this case of Lambert-Beer's law, you notice two different ways of writing the Lambert-Beer law. We ended up with a e to the negative nb delta s. And that nb delta s has a name. nb delta s is a term that taken together is called the optical depth. Now that can be a really ugly term for a lot of students. A lot of students hate that term, optical depth. By the way, the symbol for optical depth is tau. And because it's a monochromatic property of the atmosphere, it can be a different optical depth of a layer of the atmosphere for different wavelengths of radiation. So it's a monochromatic property, tau lambda. A layer of the atmosphere has an optical depth. We can describe the features of, like, this layer of the atmosphere has an optical depth of blah. Okay, it's a number. It's a unitless number, and it describes how much that layer resists the flow of the radiation through it. So, like, if a layer, it's defined so that, like, a layer that has an optical depth of 0 is not absorbing any of the radiation that's passing through it. It's transmitting all of it. And optical depth goes all the way to infinity. The bigger and bigger the number it gets for an optical depth, the more that layer is resisting the flow of radiation at that wavelength. The more it tends to absorb it rather than transmit it. And it's defined in such a way that the optical depth of 1 means that the radiation that passes through the layer is 1 over E of the radiation that was incident at the beginning of the layer. E is that Euler's E, it's 2.73 something or whatever. Think of it as being 1 over that, it works out to about 30%. Okay, but it's just a number. It's kind of like half-life or something like that. Okay, half-life is like how long a material will last before half the molecules have broken down, or half the atoms are broken down. Think of it as sort of like that, except it's a different number. It's 30%. Okay, it's how far through the material you have to go for only 30% of the radiation that's still being transmitted through it. But it's just a measure. It's just a measure of how good a layer is at resisting the flow of radiation, or sort of like the opposite of transmitting the radiation. So, for example, let's think about the optical depth of the atmosphere for shortwave radiation. Well, with the exception of things like clouds, or maybe particularly polluted situations, by and large, shortwave radiation from the sun is generally transmitted through the Earth's atmosphere. The transmissivity of the atmosphere is pretty high. You know, I mean, for a few wavelengths within the shortwave part of the spectrum, you know, like ultraviolet and so on, the atmosphere is actually pretty good at absorbing it. But for most wavelengths of, like, visible light, the atmosphere actually has a transmissivity quite close to 100% or 1 or whatever. It's not exactly 1, though. So the optical depth of the atmosphere for shortwave radiation is pretty small. By and large, the atmosphere doesn't resist the flow of shortwave radiation very much at all. A little bit. Some is absorbed by aerosols and some gases and so on. So the optical depth of the atmosphere for those wavelengths, tau lambda, it's greater than 0. I mean, the atmosphere doesn't completely transmit this radiation, but it's much, much less than 1. Okay. Certainly, the vast majority, under clear conditions, without a lot of pollution or whatever, the vast majority of shortwave radiation that is not ultraviolet, that is an incident upon the top of the atmosphere, does make it all the way to the surface of the Earth. Okay. Just as another example here, if you look in the picture here, there's a layer of altocumulus clouds, altostratus clouds, which you may or may not remember from classes like ATSEVS533, but they're fairly thick, and they don't really let a lot of sunlight through. In fact, you can actually look, I don't recommend looking directly at the sun, but you can, you know, take a glimpse directly at the sun right through altostratus clouds, and you can actually see the disk of the sun a little bit and so on. I mean, you can still see the sun. Clearly, some shortwave radiation is being transmitted through that layer of altostratus clouds. So clearly, the transmissivity of that layer of clouds is greater than 0. Right? Some radiation does get through those clouds and to your eye. On the other hand, not that much. Realistically, the amount of radiation being transmitted through that layer of altostratus clouds is not that much compared to what was incident upon the top of that layer. Most of it got absorbed or reflected or something like that. It was attenuated, it was lost. So clearly that layer of altostratus clouds has a transmissivity less than 1. In fact, probably a lot less than 1. So probably here the optical depth of that layer of altostratus clouds is probably pretty high. You know, if an optical depth of 1 means that 30% of the radiation gets through, well, I think probably if 30% of the radiation from the sun was still getting through those clouds, you wouldn't be able to look at those altostratus clouds without burning the back of your eyeball, right? So probably even less than that's getting through. The clouds are more resisting the flow of that shortwave radiation. Maybe it has an optical depth of 10 or 15 or something, or, well, not infinity, because some radiation is getting through. But it's big. It's a big number. Big, like as in much bigger than 1. So something that is completely opaque, like the ceiling in this room, exactly 0 radiation from the sunlight outside is making it through this roof. The optical depth of this roof is infinite. The transmissivity of this layer of the roof of my house is 0. Well, monochromatic transmittance, monochromatic optical depth. Obviously, other types of radiation, like long-wave like radio waves and so on, that bring cell phone signals and so on, clearly can make it through the roofs and so on. But at visible wavelength, none. Not 1 photon of sunlight makes it through this roof. Okay? So the optical depth of this roof is infinite. It is completely stopping all of the radiation from the sun, of those visible wavelengths. This trick of describing features as being optically thick or optically thin is everywhere in atmospheric physics. The atmospheric physics community loves to describe, for example, clouds in terms of being optically thin, or meaning that they let most radiation through, or optically thick, like they absorb most of the radiation and let very little transmit through. This word optical comes to us from this idea of thinking of it as like radiation as in light. But it can be, I mean, the optical depth with respect to long-wave radiation, okay, where we're talking about how much of the long-wave radiation being emitted by the surface of the Earth makes it through this layer. It's optical in the sense that it is referring to waves in the electromagnetic spectrum. But it's part of the way we describe fog. Fog is described in terms of the visibility, how far you can see in it. Well, that's very closely related to the idea of optical depth. How far can you go through this path, through this attenuating medium, and still make out the radiation, you know, that is being emitted by the headlights of that car or whatever. The same is true of gases. Describing layers that contain certain gases, like, you know, like the ozone layer. We can describe the optical depth of the ozone layer for ultraviolet radiation. For ultraviolet radiation, the optical depth of the ozone layer is nearly infinite. The ozone layer is incredible. Each individual ozone molecule is incredibly good at absorbing ultraviolet radiation. There aren't actually all that many ozone molecules up there, but they are each individually so good that, by all intents and purposes, nearly none of the ultraviolet radiation from the sun actually makes it to the surface of the Earth. Enough that it can still cause sunburns and things like that, but the vast, vast, vast majority of it is absorbed by the ultraviolet radiation. So we can talk about this with respect to gases. We could talk about it like, you know, the water vapor in the atmosphere, or the carbon dioxide, or the methane, and how it works to resist the flow of electromagnetic waves at particular wavelengths. So as we divided our atmosphere up to make some kind of n-layer model, it would be really stupid of me to just sit around and try to guess what I think the optical depth, what I think the transmissivity of each of these layers is for shortwave radiation, for longwave radiation, for each of my 2 streams of radiation moving through it. A much better idea is to actually get some information. Go and measure what is the concentration of greenhouse gases in each of these layers. Or what are the concentration of ozone, or what are the concentration of water vapor liquid water droplets like in clouds or whatever, and actually compute what is the monochromatic transmissivity of this layer for shortwave radiation. What is the monochromatic transmissivity of this layer for long-wave radiation? And stop this business of just guessing. and like trying to adjust and trying to think about it in terms of that slide from NASA. No, let's actually compute it. Let's find out how thick we want to make each of these layers. Like I'm dividing the atmosphere up into layers, and the first layer goes from 0 to 500 meters, and the second layer goes from 500 meters to 1,000 meters. And in each of those layers, let's do a field campaign. Let's get out there with instruments and measure the density, the number density of different greenhouse gases. And in the lab, we can figure out what their attenuation cross-section is, B, and so on. And we can actually figure out then what the transmissivity of each of these layers is. And then we can just use those numbers in our n-layer model, where we're going to be creating a system of n equations and n unknowns, which will be a real pain in the butt to actually compute, but that's what computers are for. That's why these models are done on computers, because it's not really something your high school math classes get to beyond about a problem of 2 equations and 2 unknowns, or 3 equations and 3 unknowns. And then in practice, we're treating this like this isn't something that changes, but in practice, the number densities of these greenhouse gases change from moment to moment. I mean, water vapor, for example, is a greenhouse gas. Well, clearly, sometimes the air is more humid and sometimes the air is less humid. And for that matter, an important contributor to the greenhouse effect is clouds. Well, clearly the amount of cloud in each of these layers could change. So this is something that we're going to have to compute, like in our model, with respect to time. As conditions are changing based on the weather and so on, we're going to need to recompute this radiation model each time as the water vapor in the atmosphere changes, as the cloud cover changes, and so on. But you would think we could at least generalize here. You would think we could at least say, yes, but okay, as we add more and more greenhouse gases to the atmosphere, the optical depth for all these layers is increasing, and less long-wave radiation gets through, and that all just sounds wonderful. And if I could get a 100-level student to tell me that in like ATSEVS533, the Science of Climate Change, I'd be thrilled. But it's not exactly what you're learning here in the 500-level version, because we're failing now to think about this in a monochromatic way. At different wavelengths, this is going to have different effects. You're right, overall, increasing the amount of greenhouse gases in the atmosphere is going to increase the optical depth of the atmosphere with respect to long-wave radiation, but it's a complicated story. I mean, going back to a slide we saw last time, where the top figure was a depiction of how much long-wave radiation is being emitted by the surface of the Earth at a range of different wavelengths shown on the x-axis, and the second panel down there was how much that radiation is being transmitted. Well, like for example, at the 2 ranges of wavelengths that I have highlighted in blue, the Earth emits plenty of radiation of those wavelengths and already transmits virtually nothing of it. The concentrations of greenhouse gases that we already have in the Earth's atmosphere make the atmosphere opaque to that types of radiation already. Already the optical depth of the atmosphere with respect to radiation at a wavelength of, say, 6 microns or 14 microns or 15 microns is already infinite. That optical depth is already infinite at those wavelengths. Adding more greenhouse gases can't make it bigger than infinite. Okay? Increasing the greenhouse gas concentration doesn't change that at all. In the same sort of way, there's a big chunk of the electromagnetic spectrum between about like 8 microns and about 14 microns, maybe 13 microns, where, again, looking at the top diagram there, the Earth's surface emits a lot of radiation at those wavelengths. And looking at the bottom diagram there that shows how much is transmitted through the Earth's atmosphere, well, by and large, the atmosphere, the gases that are in the Earth's atmosphere, like carbon dioxide, water vapor, and so on, don't, in general, absorb very much of that at all. I mean, sure, at these wavelengths, we already have an optical depth that's basically 0. The atmosphere doesn't really resist the flow of this radiation all that much with the amount of greenhouse gases we already have. Yes, I suppose if we add more greenhouse gases, we will slightly decrease the amount of this that we are transmitting, but the already 400 parts per million of carbon dioxide we have in the atmosphere already barely stops any in those ranges. That's why this is the atmospheric window, if you remember that term. So adding another 40 parts per million might change its transmissivity from 0.99 to 0.985 or something, which might be important, but isn't exactly going to shake the radiation budget of the Earth vastly. On the other hand, if we continue going, remember how there were some parts of the electromagnetic spectrum, somewhere near 4 microns, somewhere near about 7 microns, and somewhere near about 14 microns, where the Earth, looking at the top panel there, the Earth certainly does emit radiation at those wavelengths, and at the concentrations of greenhouse gases we have in the Earth's atmosphere now, we absorb some, but not all of that radiation. We absorb, let's just say, 50% of it. We have an optical depth of somewhere in the ballpark of 1 for those wavelengths. Well, increasing the concentration of greenhouse gases in the Earth's atmosphere will then continue to increase the optical depth of those layers. Less and less of that radiation will get through. These are the bands we need to worry about. These are the parts of the electromagnetic spectrum where the Earth is emitting radiation, and our atmosphere currently absorbs some of it, and there's room to make it worse. If we keep increasing the amount of greenhouse gases in the Earth's atmosphere, we will continue to make the optical depth greater and the transmission of that radiation less. So, to think about this here, one way to think about the processes that are maintaining the temperature and the climate and so on is to think about the ways in which the anthropogenic greenhouse gases are changing the optical properties of the atmosphere. Atmospheric physicists love this kind of stuff. They can do it in terms of greenhouse gases, but they also love to talk about it in terms of like changing the constituents of the atmosphere after a major volcanic eruption, or water vapor that's added to upper atmosphere due to rocket launches and so on, and partially combusted fuels and things like that. All of which has the capacity to change the optical properties of the atmosphere. Optical as in how radiation moves through it, not necessarily visible light, could be long wave or whatever. And that has ways to change the temperature, structure of the atmosphere, and finally the flux of radiation at the surface of the Earth, which is another way of saying the temperature of the Earth. Now, in the third part of this lecture here, we're going to start looking at one of the tools climate scientists use to take this idea of changing the optical properties of the atmosphere and how that results in a temperature change. But before we get there, let's answer 3 quick questions. Question 4. The optical depth is a monochromatic property of an object, true or false? It's really that word monochromatic I would just care about. Everything else you can say was okay. Is it a monochromatic property or not? Make a choice from those 2 options and get a little feedback before we move on to question 5.